at night.
This is the Space Telescope Science Institute at Baltimore, near Washington. It's from here that the Hubble Space Telescope is run. It's named in honor of Edwin Hubble, the great American astronomer who first showed that the universe is expanding. 40 years after his death, the telescope named after him is making a series of spectacular discoveries. Launched into an orbit 300 miles above the Earth, where the seeing is perfect all the time, it was expected to outperform any ground-based telescope. And despite the fault in the mirror, it has done so. It was also designed to be serviced from space. And in December, this is going to happen. Some of the present instruments are going to be replaced, and corrective optics are going to be installed to compensate for the fault in the main mirror.
The mirror was made perfectly wrong. They built the mirror with the incorrect prescription for the telescope. So the mirror has been built to a very smooth, very perfect shape, but with not the right conic constant. That means that rays that hit the edge of the mirror are focusing at a different place that rays hitting the center of the mirror focus. And the result is a blurry image, an image that's comparable in diameter to the images that we get from ground-based telescopes, instead of being about 10 times better.
What have you done to compensate for the error?
Well, since launch, we've still been able to take very high-resolution pictures by processing the images from the spacecraft. The images actually do contain information at very high spatial frequencies, at very small scales on the sky, but that information is buried in the fuzz from the rest of the mirror. So that's extracted by computer processing.
What's being done about the various other problems with the telescope, quite apart from the optics?
Well, the pointing system has a few problems. It's not as stable as we would like due to some jitter from the solar panels, and those will be replaced as part of this mission. Will also extend their life. We also have some problems with the gyroscopes, which are responsible for holding the spacecraft in a stable configuration, and those will be replaced.
We've heard a great deal about Costar. What exactly is that, and how does it work?
The Costar is short for the Corrective Optics Space Telescope Axial Replacement. What it is an instrument which replaces the existing high-speed photometer in the focal plane of the telescope and deploys optics in front of all of the other apertures at that level in the telescope. The light, instead of going straight into the apertures of the other instruments, now has two bounces off mirrors in Costar, and those two bounces correct the image and make it look exactly as it would have done had there been no problem with the primary mirror. And the most delicate parts of the operation, which is the optics alignment, will all be done after the spacecraft is released from the shuttle, and we're able to control it from the ground and align the mirrors with little motors on the mirrors after everybody's left it behind. So the most delicate part is done in a very stable and quiet environment.
The servicing mission in December is going to be the most delicate and dangerous operation ever carried out in space by astronauts.
First of all, we need to ensure that the Hubble telescope as a satellite observatory can survive for another few years. We're going to visit it periodically, so it needs to survive until the next shuttle flight. And that involves changing out some of the gyros and some of the other electronic components. But of course, the thing that people are most concerned about, and I as a former astronomer and yourself I'm sure are absolutely keen on fixing the telescope's optics so that we can get the view of the universe which we've been waiting for so long. Despite, of course, the many, many good things that the telescope has been able to do, we still want to be able to see out to the edge of the universe, and that's hopefully what we'll make possible.
Are you going to have problems in carrying out very delicate adjustments when you're wearing space clothing?
Right, now some of the mirrors which we're putting in to correct the optics really have to be positioned to a fraction of a millimeter, and I can't even do that with my fingers, much less gloves. I like to use a little demonstration to show people, though, how we can do it. We call this a Hubble telescope simulator, very high-tech equipment. It's a ballpoint pen, and I'm going to put the point out. Now this point, if you actually look at it, is positioned to an accuracy of greater than 1/10 of a millimeter. It slides in a track, and if you get it started in the right direction, then the the way it's put together ensures that it ends up with the required accuracy. And that's the trick with the Hubble telescope.
What would you say are the chances of getting everything done?
Well, everything done. Let me, actually, these tasks have been very well designed for space-suited crew members because, of course, the Hubble Space Telescope was always designed to be taken care of in orbit. So there isn't any of these tasks which I would look at and say that if it goes the way it was planned and designed, we shouldn't be able to finish it. So I'm confident that the tasks are all doable. But the other thing, and I say this on the basis of having been in space 3 times, I'm also confident that things never seem to go quite as they're planned.
A few miles from Baltimore is the Goddard Space Flight Center, and it's from here that the telescope is actually operated. Instructions are sent from Baltimore to the control room here at Goddard, and from here commands are sent out to the telescope. And so this is very much the nerve center of the entire operation.
Over the past 2.5 years, we've spent very little time in what we call safe mode, which is a non-productive mode, and we're actually getting a science return at 33% efficiency out of a possible design limit of 37%. So all in all, I would say that we're working very well in spite of all the problems we've had.
I know there have been problems with the gyros. What's the situation there?
Yes, there have. There are 6 gyros on board, 3 of which are required to carry out the science program. 3 of the gyros to date have failed. 2 failures have been a result of using some technology that had some generic problems with it. One of the set of gyros has new technology gyros on board, and we haven't had any problem with that particular gyro. So the intent is to replace at least 2 of the gyros on this upcoming repair mission and giving us as a minimum 5 good gyros when the shuttle leaves. That should restore our gyro capabilities and provide enough redundancy to carry us well beyond the 97 servicing mission.
Much of the equipment we used in the December servicing mission is being tested here at Goddard. How is that going?
The testing is going very well. The plan is to make sure we have all mechanical and electrical compatibility that can be verified on the ground tested before we bring it up on orbit to preclude mistakes. We have a hi-fi mechanical simulator that represents the precise mounting and installation, and we have an electrical simulator that represents all of the electrical connections and interfaces between Space Telescope and the replacement hardware and the ground system. There are no incompatibilities, and everything is going as designed and as expected.
But Hubble has already proved its worth. In the 3 years since being launched, it has produced outstanding scientific results. For example, it has been used to study those mysterious objects, the black holes.
Black holes are important because they are the engines that power the release of energy that we see in the centers of galaxies. And one such galaxy is NGC 4261. And what you see in the left-hand panel of this image is 4261 in the Virgo cluster. The white ball that you see in the center is the light from several 100 million stars that make up the galaxy. The other small white blobs of light are other galaxies in Virgo, and the double jet that you see illustrated in orange is a superposition of a radio map from the Very Large Array in New Mexico, and it shows that the energy released in the center of this galaxy is collimated in a bidirectional flow that goes out to a distance of some 30,000 parsecs, spanning enormous distances in the cluster. Then we zoom in with the Space Telescope, and we see in the very center of this galaxy a dark disk surrounding a bright spot, and we believe that that dark disk is dust and gas. In fact, we know that it is dust, and we know that there is neutral hydrogen and carbon monoxide in this, and it is surrounding the bright spot in the center, which is the location of the black hole, and that disk is the fuel supply for the black hole, and taken together it's the engine that produces the optical and radio emission which we see.
The other night, I was using my modest telescope to look at M51, the Whirlpool galaxy, but there could be a black hole there.
Yes, there is a radio source in the center of M51. With the Space Telescope, we discovered that there is a dust lane that bisects the nucleus, and we think the black hole is hidden behind this dust lane, which may be an edge on disk.
What about M87, a much more massive galaxy than the Whirlpool?
Yes, M87, Messier 87, is the second brightest elliptical galaxy in the nearest large cluster of galaxies, the Virgo cluster. It has a very similar appearance. That is, it is a round ball of stars. In this case, it is probably 100 billion stars bound together gravitationally. And in the very center, there is a bright radio source that produces a radio jet in M87.
What about other objects you've been looking at with Hubble? I'm thinking of Markarian 315.
This galaxy, which has an active nucleus that is probably a black hole being powered by gas falling into it, that the nucleus is actually two nuclei. These two nuclei are in orbit, one around the other. One is spiraling into the other, and the interaction of the two nuclei is stealing angular momentum from the gas around the black hole, which allows it to fall into the black hole and fuel it.
Then there's that superb picture of Hen 1357.
Yes, that is a picture of a very young planetary nebula that was taken by Matt Bobrovsky at CTA here in Maryland. And what he sees in that is a ring and a pair of blobs along the axis of the ring, and this is probably showing us how this end state of stellar evolution, where the core of the star is contracting towards a white dwarf and the outer envelope has been blown off, it is probably showing us the details of how the morphology of this shell of ionized gas is determined.
What about a much more violent stellar death, the Cygnus Loop?
Cygnus Loop is the result of a star that imploded upon itself. The core of the star imploded some 15,000 years ago, and in that implosion it released an enormous amount of energy which blew the outer envelope of the star away, and this process is called a supernova event. That shell expands at some 10,000 kilometers per second, and as it expands, it sweeps up gas from the interstellar medium, and that gas that is swept up, since it is encountering this shell at several thousand kilometers per second, is ionized, and as a result of the ionization, it's heated to a high temperature, it emits light, and we see this beautiful shell. The significance of these observations is that we can see the details of the interaction of this expanding shell of hot gas with the interstellar medium.
One of the main projects for the telescope is the study of very distant objects. Because of the problem with the mirror, Hubble has been able to see, but not resolve, objects as far away as 10,000 million light years. All the same, it has been responsible for important advances in our understanding of the evolution of galaxies.
We take a long exposure as possible on a random piece of sky and then look at the numbers of the galaxies that we see and the shapes and sizes of those galaxies. And what we're beginning to find is quite a lot of evidence for interactions of galaxies in the past. That is, galaxies seem to be merging together. And so that is one way in which the Hubble Space Telescope is helping us to understand how galaxies got to be the way they are today.
But you're also using observations made with ground-based telescopes.
That's certainly true, and in fact we still use ground-based telescopes to follow up on the work that we're doing with the Hubble Space Telescope. For every deep image, for instance, that we obtain of one of our random sky fields, we spend many nights of telescope time to get images in different colors so that we can understand what kind of stars are in those galaxies, and also to try and go deeper from the ground-based telescopes than we can with the Hubble.
By deeper, I imagine you mean further away, because after all there are many ground-based telescopes larger than Hubble.
That's right. So what we do is we try and get as much telescope time as we can on the very biggest ground-based telescopes, such as the Kitt Peak Observatory or the AAT or the William Herschel or the Keck telescopes, in order to try and go as deep as we can, that is, find the faintest galaxies that we can from the ground, so that we can determine exactly what we're finding with which of those galaxies we're seeing with the Hubble Space Telescope.
One of Hubble's main instruments is the Wide Field and Planetary Camera, which images planets as well as other objects. During the coming service mission in December, the present camera is to be replaced with a completely new one.
Well, the planetary camera, wide field planetary camera, suffers from the same problem as the other instruments on Space Telescope. Unfortunately, it's not corrected by the Costar. Therefore, we're going to correct it separately by replacing it with a new version, which was actually under construction at the time of launch. Fortuitously, the primary mirror is actually imaged onto one of the little mirrors inside this camera. So by changing that mirror, we're able to exactly correct the beam and end up with the images that we would have had there been no problem with the primary mirror.
What have been the most important results to date?
Well, an example is the observations of the storms on Saturn. From the ground, we noticed that something strange was happening on Saturn. A white spot appeared to have appeared on the surface of the planet, but nobody really knew what was happening. So in very short order, HST was slewed to look at this, and we took a series of images in color which showed that the storm had developed around the equator of the planet and extended indeed almost a third of the way around the planet. This was one of the original objectives of a space telescope, to be able to take images of at short order of planets. It's an advantage we have over, for example, the Voyager missions, which have to look at a planet as they pass it. We can look any time we choose.
What about Mars and Jupiter?
On Mars, we've been looking at dust storms. We've been looking at Mars periodically. Obviously, we get much better resolution in general of the surface than you can from the ground. And again, you see it whenever you choose to look at it. On Jupiter, we're able to get images of comparable quality to Voyager. And that's enabled people to look at the evolution of the planetary atmosphere, particularly, for example, around the great spot. One can see vortices trailing away from that great spot and study their time evolution.
What about the volcanoes on Jupiter satellite Io, discovered from Voyager? They've been imaged by Hubble, have they not?
The volcanoes have, although we haven't seen the plumes of material coming from them, directly from them, as you did in the Voyager image. What we have seen are surface features in the ultraviolet, and been able to compare those with the Voyager images, which were taken in visible light. It turns out that in the ultraviolet things are bright, where in visible light things are dark, and vice versa. And from that observation, we're able to determine the material that's on the surface of the planet.
There are 5 main astronomical instruments aboard Hubble. One of these is European. This is the faint object camera. And this has probably been more affected by the mirror fault than any other instrument. And yet it has produced some of the most spectacular results.
Well, I've been involved together with a number of people from this institute and from outside, particularly Alan Sandage and Gustav Taman, in observing a galaxy called IC 4182. We chose it because we could observe both the Cepheids and because we knew there was a supernova there that was observed, well studied in 1937. And so through the determination of the distance of that particular galaxy, IC 4182, we can determine the distance, the absolute brightness, therefore, of the supernova. And through this one supernova, then the whole curve can be normalized. And we can determine then the expansion rate of the universe. It turns out that it's a value 51 plus or minus the error that would make, give or take, some 51 kilometers per second per million parsecs. This is a low number for, or is in the low range of the numbers that have been accepted for the expansion rate of the universe. And it's very important because a high value for the Hubble constant, if we had measured 70 or 80 or larger number, would have meant a universe that is a lot younger than some of us would like it to have. Certainly young enough that would be incompatible with the age of star clusters like globular clusters in our galaxies, which you know are the order of 12 billion years old. This determination of the Hubble constant of 50 plus or minus a few tells us that the universe is definitely older than that, we know that, but is more of the order of 15 or 17 billion years old. So it is a very important first step, but I want to emphasize it's a first step.
How much more detailed do you think the results are going to be when the new lenses are fitted?
Well, certainly a great deal more precise. We would like, and we will continue to carry out this experiment of measuring the Hubble constant through Cepheids and other standard candles at larger and larger distances. You have to be able to see objects that are much fainter than we can look at today, or that are closer together, where the wings of this point spread function, the wings, the halo around the bright star, doesn't affect the faint objects next to them. That is certainly a key correction that the telescope will undergo, both in the wide field camera and in the faint object camera.
Hubble's been making very interesting observations of objects inside the Orion Nebula.
Well, This is a very, very interesting set of observations. They were done by Bob Odell from the University of Texas. And he was studying a number of stars in the Orion Nebula close to where you can see the cloud evaporating because of the radiation from newly born stars close to the nebula. And as he was studying the nebula itself, what he saw was that around a certain number of stars, there were some disks. And so if it hadn't been the nebula behind, he would not be able to see them. And these disks are protoplanetary disks. This is material that is still falling around the star, is presumably going to be forming planets if you give them enough time. These are very young stars. They're not older than about 1 million years or so. And so they haven't had enough time for this disk of gas and dust to make planets. But if we could wait long enough, we will see the planets. And so it's very exciting because it's telling us that in our galaxy, close by, only about 1,500 light years away from us, there are at least 20 or 30 stars that have got planets around them, or protoplanetary systems.
There are 3 European elements in the Space Telescope. How have they performed?
Well, I would say in truthfulness, with mixed results. The solar rays have performed very well from the point of view of the amount of power they provided. They had some small problems associated with the fact that they bend more than we expect them to bend as they go in and out of the sun, and they cool and warm up a little bit faster than they should, and therefore they introduce small pointing jitter in the spacecraft.
When the new solar panels are fitted, I imagine they'll be modified to avoid the same fault happening again.
Yes, indeed, Patrick. ESA has spent a lot of time and effort and money as well into to try to solve this problem, and indeed they have. They've modified substantially the way the solar rays were built. They modified it by putting a sleeve over the booms that extend during the deployment, and these sleeves will compensate for the thermal effects as you go in and out of the shadow of the Earth. The faint object cameras perform very well. Unfortunately, the telescope in front of it is not giving us the image we would like to have, and we certainly look forward to the repair mission, to the maintenance mission, in order to improve that performance. The third element is the people at the Space Telescope Science Institute, the European astronomers that are working here all the time, and I think we're performing very well, but that's not for us to say.
So we look forward to December and the repair mission to the telescope. Don't expect any immediate results. It's bound to take some weeks or even months to get everything properly working, but the outlook is bright. You know, many people have made far too much about the fault in the main mirror. Of course, it was unfortunate, but just look at what the telescope has achieved. It's shown us things we've never seen before. It's been responsible for fundamental advances, and perhaps most important of all, it's shown that space telescopes do work. There's absolutely no doubt that it's going to go down in history as one of the most successful pioneering instruments of all time. Meanwhile, we look forward to bringing the sky at night back to Baltimore and giving you the latest news about discoveries made with this remarkable telescope.